Welcome to lecture number 11 for EE 206, Circuits 1, Thevenin equivalence and max power transfer. Now, in our last lecture, we looked at Thevenin equivalence. That's taking a circuit and representing it by a voltage source and resistance, two elements that give you the same load line, same voltage versus current relationship. The circuits we looked at before were fairly simple. The ones we'll look at today will be a little bit more complicated. It's the same idea. I've got a circuit like this. I want to represent it with a voltage source and a resistance such that I get the same load line. Prior, what we did is do the open circuit test to find V Thevenin, do the short circuit test to find I Norton, or turn off the sources and measure the resistance looking in. Same idea here. The problem with this one is that if I turn off the sources, measure the resistance looking in, I don't really know what to do with this current source, this dependent current source. So what I'll do instead is apply a test voltage. Apply a 1 volt test right here and see how much current it draws. If it's 1 ohm, 1 volt will draw 1 amp. If it's 100 ohms, 1 volt will produce 1/100th of an amp. So by measuring the current, I can tell you what the resistance is. That's actually how an ohm meter works. An ohm meter applies the test voltage and measures the current. From that, I can tell you what the resistance is. So, given a circuit like this, find the Thevenin equivalent. The first step is find V Thevenin. So what I'll do is I'll find the open circuit voltage, and that's just a voltage node equation. I'll assume V1 and find the voltage so that everything balances. The current left is V1 minus 5 over 3K. The current through here is 100 or minus 100 IB. That's the current from the node. IB is actually 5 minus V1 over 3K. So it'll be minus 100 IB plus V1 over 5K. That's got a balance. And one way to think about this with these arrows, if I flip the arrow on IB and I flip this arrow, I get a double negative. That also works. So you could think of it as V1 minus 5 over 3K plus 100, V1 minus 5 over 3K plus 5K equals 0. And you notice I get this double negative in there. That works out the same. Solve for V1, and I get V1 is 4.97 volts. So that's V Thevenin. Okay, so far so good. Now to find R Thevenin, I'll turn off the source. This becomes 0 volts. This doesn't turn off. That's a current control current source. If IB changes, this changes. Now measure the resistance looking in. That's not really obvious, so let's apply a 1 volt test voltage and calculate the current. The current will be 1 volt over 3K, that's this current, plus 1 volt over 5K, plus 100 times 1 minus 0 over 3K. Or since this is going up, it's like a double negative. Minus 100 IB, IB is 0 minus 1 over 3K. Put it all together, I get the current, the three currents add up. I get a total of 33.87 milliamps. The resistance then is 1 volt produced a 33 milliamp current draw, so it must be 29 ohms looking in. So the Thevenin equivalent is 4.98 volts and 29 ohms. Second example. This is actually an op-amp circuit, something we'll look at in a couple days. I've got a voltage-controlled voltage source, that's an op-amp, and a couple of resistors. Find the Thevenin equivalent at point A. Basically it's saying, looking at an op-amp at the output, what does the circuit look like? To do that, I need to find the open circuit voltage and the Thevenin resistance. To find the open circuit voltage, I'll write the node equations. V1 minus 1 over 1K plus V1 minus V3 over 10K equals 0. And node 3, V3 minus V2 over 100 plus V3 minus V1 over 10K equals 0. And V2 is minus 1000 V1. Three equations, three unknowns, solve. And what you get is V3 is minus 9.89 volts. That's V Thevenin. Now to find R Thevenin, I turn off the voltage source. There's my 1 volt goes to 0. Find the resistance looking in. And again, that's not obvious, so what I'll do is I'll apply a 1 volt test voltage and calculate the current that it draws. To do that, I'll write the node equations again. V3 is 1 volt. So B3 minus B2 over 100 plus B3, these are in series, over 11K equals 0. B1 is, by voltage division, 1/11 of B3. And if I know B1, I now know B2. Once I know B1, B2, I can calculate the current. It's 919 milliamps. The resistance then is 1 volt produced 919 milliamps. This looks like 1 ohm looking in. This is a little bit deceptive. That 100 ohm resistor might make you think that this looks like 100 ohm resistance looking in. It's actually not. It's only like 1 ohm as the Thevenin resistance. So this circuit has the following Thevenin. Looking in from point A, I see 9.89 volts and 1 ohm. Okay, so that's kind of generalized Thevenins. You can do the circuits like we did yesterday, or a little more complicated ones. If it isn't clear what the resistance is, apply a 1 volt test voltage. Where Thevenins are useful is as follows. Suppose I've got a circuit, could be any circuit, it'll have some Thevenin equivalent. I want to connect a load to it. What load maximizes the power to the load? The reason I might want to do that is this circuit could be a solar panel. I want to get as much energy out of the solar panels as I can. How much can I get? This could be a stereo. I want to connect a speaker to my stereo and get the maximum power out. What resistance for the speaker maximizes the output power? That's the idea behind max power transfer. And you know there's going to be a maximum. Let's take the limits. If I have this circuit, let RL be general. The current is V Thevenin over R Thevenin plus RL. The power is I squared R. So the power is going to be RL over R Thevenin plus RL squared times V Thevenin. The maximum is when the derivative is 0. If RL equals 0, the power to the load will be 0. There's basically no voltage. If RL is infinity, there's no current, and again the power is 0. So 0 and infinity give you 0 power out. Somewhere in the middle, there's a maximum. This is where the maximum happens. When you take the derivative with respect to RL, set it equal to 0. That actually has two solutions. RL could be minus R Thevenin, or RL could be plus R Thevenin. Plus R Thevenin is the max power to the load. Minus R Thevenin is actually minimum. It's the max power transfer back to the source, which is also hard to implement because it's a negative resistance. So the one we're looking for is RL equals R Thevenin. As a check, in MATLAB I can just say, let's sweep RL and see what happens. And MATLAB would say Vn is 12 volts, R Thevenin is 2 volts, just kind of as an example. Let's have RL go between 0 and 10 ohms of steps of 0.01. The current is voltage divided by the total resistance. And note I need to use this dot notation. This is a matrix. If I don't put that in there, it'll try to do a matrix division. This doesn't make sense. That's not a square matrix. Dot slash tells MATLAB, don't treat this like a matrix. Treat that as 1,000 different entries. Do each one by one. So this is element by element division. Once I have the current, power is I squared R times RL. Again, using the dot notation. Take the current at each element, square it, multiply by each element of RL, that gives me the power, as RL goes between 0 and 10. When I plot it, I get this curve, and note the maximum's right here at 2 ohms. So max power transfer is when the load is equal to R Thevenin. Slight caveat. If I can vary the load resistance and R Thevenin is fixed, the load that I want to maximize the power is RL equals R Thevenin. A slight problem with that is I'm at 50% efficient when I do that, but that is max power transfer. A slightly different problem is, suppose I could vary R Thevenin. RL's fixed, R Thevenin is variable. What R Thevenin maximizes the power to the load? And some textbooks will say R Thevenin equals RL, problem solved. That's actually not true. This is the output impedance of an amplifier. Ideally, I want this to be 0 ohms. If this is 0 ohms, all the power goes to the load. I don't want to increase the resistance to the amplifier if I don't need to. And actually, the maximum power is when R Thevenin equals minus RL. If that's true, the current's infinity, and the power's infinity. So what I want to do is get as close as I can to R Thevenin equals minus RL. If I can't have negative resistance, then let's set R Thevenin equal to 0. That's the closest you can get to minus RL. And if you want to make sure, let's plot it. Suppose V Thevenin is 12 ohms, RL is 2 ohms, and R Thevenin can go anywhere between 0 and 10 ohms. Saying I don't know what the answer is, let's just calculate all of them. Find the current, find the power, and plot. Here's what the power of the load looks like. It's approaching an asymptote at minus 2 that goes to infinity. The peak will be right here at 0. So if I can vary the output impedance of an amplifier, what I want is 0 ohms. If I can vary the impedance of the load, I want to match R Thevenin. That's max power transfer. Third problem. Instead of trying to maximize power, let's maximize efficiency. The efficiency is the power to the load divided by the total power dissipated. That's going to be the power to the load, I squared R, divided by the total power, I squared times R Thevenin plus RL. The I squareds cancel, so I get RL over RL plus R Thevenin. The maximum is when RL equals infinity. There the efficiency is 1. Saying if I draw 0 current, if RL is infinity, I have maximum efficiency. There's 0 power to the load, but the efficiency is 100%. That's kind of one problem you have. The max power is at 50% efficiency. Half the power goes through R Thevenin, half goes to the load. Max efficiency is when I have 0 power to the load. So you really can't have both. I can't have maximum power and maximum efficiency. You got to pick one or the other. That's kind of where Thevenin equivalents are useful. With a Thevenin equivalent, I can see how the load resistance affects the efficiency and the power, versus a more complicated circuit would make it much harder to see. And with that, I can see the basic rules. If I can vary the load, R load matches R Thevenin. If I want to vary R Thevenin, make R Thevenin 0. That's lecture number 11, Thevenin equivalence and max power transfer.